So I think we said good evening. Good evening. Can you hear me? Hello. Can you hear me? Okay. Okay. Great. Okay. So you're all welcome to today's session. As usual, we would go into um, the stuff we've been doing. This week we are going to go more into systems of linear equations, and then I think that's what leads us to regression. So, can anyone tell me anything about what they learned last week before we briefly move on? Anything on last week? Anyone would like to volunteer? Talk about what we did last week? No one? We are not many, so you can just unmute your mic and talk. If you are Emmanuel, Manal, I think Bismarck. Which lab are you from? Are you from Vectors? Okay. So I think we learned the same thing. So can you give us a gist of what you learned last week? Manal and Emmanuel, I'd like to hear from you too before I just start. Okay, so not to waste much time, last week we were working much on matrices and linear transformations. So we are going to see how that builds up into leading to solving systems of linear equations and then moving on to regression. So basically that's what we are going to be doing today. So you're welcome to this session by Vispad Institute of Technology. This is lab 6, I guess, yeah. So for today's lab, the major outcomes we are looking out for will be linear systems, understanding linear systems in machine learning, understanding Gaussian elimination, matrix inverses, and how to solve them, and also things like numerical stability and alternatives. Okay. So all of these will help you understand more about what machine learning is all about. Now, for this first block, I don't think I need to explain much about it because we've seen it over and over. But just to be sure that everyone is on the same page, can someone explain what's happening on this block 1? Of course, we understand import NumPy and then import matplotlib as PLC. I think we understand those two. Can anyone explain the next 3 lines? Please just unmute your mic and talk. Anyone? Okay, so let me take you through. So the third one, which is hashtag percentage sign or mode matplotlib inline. Sorry, I keep saying MATLAB. And then so that one allows the images you are going to generate to just show directly under the code instead of showing separately. The next one, so our preprint options, we are setting precision to 4, which means that 4 decimal places, and then suppress equals true, which means that if you have a decimal that's very small, you should just estimate it and give you 0. And then these are our fixed dimensions for images we are going to be generating. So we are going to make today's lab as practical as possible. So starting with the first part, ax equals b. We've already seen this equation in the terms where A is a matrix. Is anyone trying to see something? Ahmed, Yakubu, are you trying to see something?
No.
Okay, then please can you mute your mic?
Okay.
Okay, thank you. Yeah, so let's get back into it. So we are on our linear systems. This is the first part, and I am sure that last week you saw this equation format ax equals b, where a is a 2 by 2 or any matrix at all, and then b is a solution, which is also a vector. Yeah. So mostly we use column vectors for these things. And then x is an unknown vector, some vector that multiplies and then we get b. So how do we get our unknown vector? Okay, so that's where you need inverses. So now let's just start with understanding basically what it means. So first of all, with NumPy we've learned how to write matrices in NumPy, which is the first one. So we write in forms of array, and then B will be our target matrix, which we also write in forms of a single array. And then when we print these, we see that this is our matrix, which is -5 to -4 1. This is the same example that was used in the class session last week. And then B is -2 and -4. So that means that the system we are trying to solve actually is -5x plus 2y equals -2, and then -4x plus y equals -4. Now this is a simple simultaneous equation. If you look at it, you can use your eyes to do some cancellations, and then you get a value straightforward. Yeah, that's if you try to. You can simply multiply this side by 2 and then do your subtraction, and then I think you'll be getting x to be 2 or -2. Yeah, so x to be -2 actually, and then if you know -2, then you can put it inside for that one. But this is a simple scenario, right? But in actual machine learning applications, you have complex equations that you can't easily solve. Okay, so in that situation, what do? That's why you have to rely on linear systems to solve them. So first of all, let's get to what we have to do, the ground things. Now we need to find our determinants. I think we all know by now how to find a determinant. So if there's a vector, then determinant to be a times d minus c times b. So that is what we have over there. And then so the vector we declared, which is the -5 1. So this vector, let me come back so that I'm not confusing. This vector here, this a vector, take note of it because we are going to start using it. Okay, so when we are done, immediately we are done, I would send, in fact let me just send that right now. Today something is coming up, so I might not be able to be telling you all the time to code after me, right? But I've made this public, so please, you can just open it and then start following as soon as possible. Yeah, but I hope that over the past few days you've been able to get the skills as to how to do basic programming. And then this week we're not going to do pure Python implementations. We are going to use NumPy throughout, which is quite easier to use. We used the NumPy in the previous lessons to show you how that whole process works. Okay, so next we are coming to our determinant, how to solve a determinant. I've already mentioned that. So if you want to solve a determinant with NumPy, you set the determinant of a is equal to numpy.linear.determinant of a. So this linear algebra Linux it's a whole module on its own, right? And then we can now print the result. Now this whole thing is a formatted string, like I tried to explain the last time. Formatted strings are just putting a value inside the string. Okay, so f double colon determinant of a is equal to determinant a to 4 significant figures, right? So that gives us 3.40, and then if there is a unique solution that exists, it says true. If there is no unique solution, then it would have seen false. So now we know that the determinant of the matrix we are dealing with, again.
Hello.
Yes, I can hear you.
Okay.
The link is not working.
Yes. So I think when I open, they say we can't find that page.
Okay, please let me do that again. Okay.
All right.
Okay. So copy. Allow comments on it. Okay. I think something is covering it here, so I have to save. Okay. So I'm coming back to it. Okay, please try again. I think this time it should work. Let me give you a moment to do that. Please, everyone should open the link, because today I'm not going to be able to let you all code along with me as we move on. Has anyone been able to? Great. So we've not gone so far, so you can just scroll to number 2, which is determinant, because these are things we've already done, so we are just revising for now. Yeah. So if you calculate the determinant of the matrix A, you get 3. Now what are we going to do with the determinant? Okay, now first of all, let's go back a bit to understand something about transformations. Okay, now we spoke about unit vectors or unit matrices the last time, where you have ones being all the rows. Okay, so if you look at this here, this is a 2 by 2 unit matrix. From just looking at it, you see that this is a 2 by 2 unit matrix, and then what we want to do is that we want to transform that unit matrix by A, right? And then we plot it with this with these details. So just look at what we are going to have here. Now to plot any diagram, I think we've done this over and over. I think the only thing we've not done so far is subplots. I don't remember teaching on subplots. So to do subplots are basically you want to put a number of graphs on the same graph sheet, a number of graphs on the same graph sheet. So you have to define the location. So this is going to either be on the first row, first column, that maybe second row, second column, and then if it depends on the dimensions. Okay, when we get to the diagram, I'll show you. And then you can set your colors and everything as you wish, and then you can check this limit and then widen if it doesn't work so well. Okay, and then so since you have the notebooks now, what I encourage is play around with it a bit, because you're not going to be typing everything from scratch, so you can be playing around with this as we move on. Now we are going to transform this matrix, this unit matrix, by the determinant we have. Okay, so let's look at something here. So this is the unit matrix. I hope you all agree with me that this is a unit matrix. So this is a simple square matrix. Okay, and then from 0 to 1, and then 1. So it has a magnitude of 1. Yeah, it has a magnitude of 1. Its value is 1 on both axes, so this makes it a unit vector, a unit matrix, sorry, square matrix for that matter. And then we want to transform it by this sort of factor. Okay, so if you transform it, you so transforming linear equation, a linear transformation of A. Okay, and then you get some sort of parallelogram that looks like this. This is all building on what Mr. Esiama taught on Sunday. Okay, so this one basic thing you should understand about transformations. Now back to why we're finding determinant. You need determinant because you would if you have this equation, let me take you back a bit. If you have ax is equal to b, okay, where is it? Okay, if you have ax is equal to b, and then you want to find for x, then you just do ax is equal to b on a, right? And then since we are dealing with matrices, b on a is the same thing as b times a inverse. Okay, so we are going to find the inverse matrix of a. Now to find the inverse matrix of a, you need the determinant. I think we did this last week, and then this is just to show you how transformations make a vector appear differently, and then even the area it has, it also changes when you transform a vector by another factor or something like that. So we are going to use Cramer's rule, and we know that Cramer's rule takes each of the components, and then takes that determinant and then divides it by the total determinant of the vector. Okay, so now this is an example of that. So we had our vector A, which you all know, the one we had up there. So what this code is doing here is that we are trying to copy the information from that vector. Okay, so we say a1 is equal to a dot copy, and then we define our A1, which is from the beginning to index 0 equals B, and then also from the beginning to index 1 also equals B. And then what we want to do at this point is that we want to say that our x1 will be the determinant of so that A1 divided by the total determinant, which is the 3 we found, and then the x2 will be equal to NP find the determinant of A2 also divided by determinant of A. Now you find that when we use Cramer's rule, the x component, so one of them gives you your x component, which is the x1, that gives you your x component, and then this one, the y component, is your x2, so that gives you your y component too. So you get, from using the Cramer's rule, you get x to be equal to 2 and y to be equal to 4. Now if you solve this equation manually, okay, if you solve this equation manually, you can try it. If you solve this equation manually, you should get that. You can do that by multiplying the, this thing by 2 and then subtracting them. Okay, you should get x component to be 2 and y component to be 4. Okay, great. So I think we are done with that part. Okay, now we're going to use another method again to find that. Okay, we're going to use another method. So now getting to finding the matrix inverse. Okay, now to find the matrix inverse, we need to if you just want to use NumPy, you don't have to go through a whole long process to find your matrix, to find your inverse. Okay, so you can just say linear algebra dot inverse of A, of the matrix A, and then so this would be your A, right? So that'll be your A, and then your x, which is what you're trying to find, will be the A inverse times your B. Okay, now what happens is that you want to, first of all, you want to print out your inverse. Now the inverse is basically so to find the inverse of a matrix, you divide each of the components by the determinant, but then you have to switch the location of the D and A, and then negate the C and B. Okay, now that's what it has done, and it's given us this result. So that means that the matrix A we had, this is the inverse of the matrix. So with this inverse matrix, if you multiply this inverse matrix by B, which is the target vector, then you get 2 and 4, which is the same thing as what you got with the Cramer's rule. So these are two approaches to validate one thing. Now one way to also do that is through Gaussian elimination. Okay, so we can use something we call LU decomposition. LU decomposition is lower upper decomposition. It's a mathematical numerical method approach to solving systems of linear equations. So this is how you do it. So first of all, there is internal elimination, and then there's backward substitution, or forward elimination, backward substitution, depending on which books you're using. So so for the first one, we want to find the LU factor, that's the lower upper decomposition factor of A, and then for B we say LU underscore solve of LU PIV, and then for P, that's for your back substitution. Now what this will tell us will be what is the value of x using this decomposition matrix, Gaussian elimination method. What are the components you're going to get? So what are your unknown vectors going to be? Okay, so that's giving you 2 and 4. And then do we have a solution for this? Just like the previous, it says yes. So now you notice that some methods are easier to use than others. So using the Gaussian elimination and using this method, the inverse method, or using the Cramer's rule, you'll find that it is way easier to just go straight away using the matrix inverse method to find the inverse of a matrix, or to find to solve a linear differential, to solve a linear equation, not a differential. That's something totally different. So I hope you get it with these three. So all of this is reading. I will leave this to you to go and read. There's really nothing technical at this point. So it shows different techniques in MATLAB. Oh boy, I think I've been saying MATLAB a lot. Please, when I say MATLAB, if you just hear me say MATLAB, just know that I'm referring to NumPy or Matplotlib. I don't know why I just keep saying MATLAB, but this is in NumPy. Okay, so if you find some of these methods in NumPy, then you should understand what they are doing, which is better than which, and then which one should be using if you are a new learner. So you find that since we started this whole program, we've been using Lenarc.solve. I think most of the time we use Lenarc.solve because that's one of the gold standards and it's very easy and safe to use. You won't spoil anything by doing that. But for some of the other methods, you have to know how to handle a few other things. And then some of them, it depends on their frequencies. How often are they used? Yeah. So you can read this. This is just for your knowledge. Now let's get, and then so this is the solve method. Okay. So you can say that x is equal to so x of np, which is x finding x with using NumPy, will be equal to np.lenarc.solve a comma b. So to use solve to solve the same linear equation we were solving with using Gaussian elimination, matrix inverse, and then Cramer's rule, you can do that using one single line of code. In fact, you can just put print np.solve a comma b, and then you get your answer. Okay, or we can try it actually. So you can just say print I think because I've not run everything, but then if you are running, right, it should work for you. So you can just say print np.lenarc .solve, and then just put your a comma b. Okay. But when you are doing this, make sure you have what they call it, you've run all the other code, yes, or this thing will not work. It will not work not because nothing is not because it's not correct, but because you've not gotten your a, okay, and your b, your variables. It has to pick those from above. Okay, so if you have issues, just come here, run all. You can just say run all, it will run again. Yeah, great. So now next on the list, a few things I'd like you to try. So after the class, try to find, so with these ones, try to find their unknown vectors. Okay, try to find their unknown vectors. So this vector times a particular vector will give you this q vector. So over here, what we actually have here is so we have p times I don't know how to put that, some vector x will be equal to q. Okay, now we don't know x, so we want you to find x. Or in this one, you can just say that this is the same thing as saying okay, so this is the same thing as saying r times some y. Let me use dot instead. It's tricky to use dot, so let me just use the times. Okay, since we are doing matrices, dot operations can be a bit different from this. So that one will be equal to say s. Okay, so use these ones, try to solve and find answers when you get back. It will be very helpful. Now getting to inverses. Okay, now you find that when we're trying to find the solution to the linear differential equation, we used inverse. Okay, that's the matrix inverse method. So the question is it used in real life all the time? And then I think I've already given you the answer over here. The answer is no. The inverse method is not used all the time in real practice. And now the question is, why don't we ever use it in real practice? And then that stems from something called the Hilbert matrix demo, or Hilbert matrix. Now has anyone had an experience with Hilbert matrix before? Let me hear from you. Has anyone heard anything about Hilbert matrix before? Okay, so real quick, let me let you read this for yourself. So use 2 minutes, Google what a Hilbert matrix is. It might go right over your head, but it's fine. So just read it, and then let me give you 2 minutes to do that right away. So your timer will start Um, okay, so your timer will start very soon. Timer. Okay, great. So your timer has started. Use that time to try to find out what a Hilbert matrix is. Okay, so do that before I continue. So find out what a Hilbert matrix is. Yeah, so let me see if your timer is up. Oh, you still have a lot of time. Okay, so use the time, try to find out what a Hilbert matrix is. Okay, okay. It's your time. Okay, great. I think your time is up. Um, yeah, your time is up. So let me stop this. Your time is up. Okay. So did anyone find anything? Would you like to share? People, please, someone should unmute and talk because I've not heard anyone talk today. What did you find? When you read on a Hilbert matrix, what did you find?
Okay. So when I searched, this is what I got.
Mm-hmm.
So they said it's a special kind of the square matrix.
Mm-hmm.
But for it, when there's a small numerical error, it causes big changes in the result.
Yeah.
And they say to identify this matrix, sometimes you find that the reciprocal of the sum of its rows and columns in the 6 minus 1 will give you that element. So far,
Right.
that's what I've
That's
gotten
very good,
before that.
Bismarck. That's very good. Now, what he was basically trying to say is that, you see, for most matrices, okay. Okay, let me see. Esther also have a response here. With entrances being the unit fractions. Yeah, basically they are both correct. Now, but one point I need you to really pay attention to is the part of error. Okay. Now, with machine learning, you want to be as accurate as possible. You see, machine learning is already suffering with trying to be very accurate. Of course, you don't want to get 100% accuracy in machine learning training. Can someone tell me why? Why don't you want to get 100%? Okay, I'm telling you the 100% machine learning training. If you train and you get 100% for your results, it's not good. 100% accuracy is not good. Can someone tell me why?
Um, I I think with that, even in life, we don't have an ideal situation. So
Mm-hmm. Yeah, right, right. Yeah,
I think that's right.
yeah, but generally, like technically, what's the problem with having 100% accuracy? Okay, so don't worry, I'll tell you. So the problem with having 100% accuracy is called overfitting. Okay, so you don't want to have 100% accuracy because whatever you use your model, whatever you use to train the model will know all of that in detail to the point where it will not be able to identify new and different data. Okay, so now let's come back to Hilbert matrix. Okay, now this is a matrix where when you alter something very small, there is a big change. Okay, I think if you look in the representation can be represented as, I think, I over I plus j something something. Now that if you make simple mistakes, okay, or let's say for something like this, we are going to do with two approaches. Okay, so we are going to pick a Hilbert matrix and then find the inverse using the inverse approach, and then also find the inverse using LU decomposition. That's the lower upper decomposition. It's a Gaussian elimination method. Now we're going to use these two and then check the error. Okay, we are just interested in the error. Now when you do that, okay, you have all of this to yourself, so please, when you do that, try to go through this. Most of these are formatted strings. Okay, these are not important for the code to work, so you can take these ones out and then that will happen to the code. Okay, now when you find, no problem. Yeah, so what happens is that, I'm sorry, so if you check for the inverse method, you find that the error you are getting is 2.2 times 10 power minus 3. Okay, and then if you use the direct solution, you get 1.32 times 10 power minus 3. If you compare these, please come in. Guys, please, a moment. Give me a moment. Let me get back to you. Okay, Charlie, I'll be in the other room.
The other room is no. There's no.
Don't worry. Don't worry. Okay. Okay, sorry, I'm back. I hope you can hear me. Hello, can you hear me? Please show some reactions if you can hear me. Okay, great. Yeah, so now comparing the errors here, okay. If you check using the inverse approach, you get a very big error. Okay, it's not too big, but substantially bigger than 1.32 times 10 power minus 3. So this is why the other approaches are not as good. Even when you're working with normal numbers, it looks okay, but in machine learning sometimes you get complex things you have to work on, and then using inverse does not really work. So mostly stick to using the easier one. This is linear.solve. Okay, so that's what this all trying to tell you. Now we move on to lines and signed area. Okay, lines and signed area. I think this is one thing we would have spoken about last week. So let me show you the graph first, and then we get to. Now if you have these equations, we are dealing with the same equations again. Nothing has changed. Okay, now with these equations, these two systems, okay, you want to find a solution to them. Now a solution to these systems is basically the intersection of the systems, okay, where their lines meet. So this is what you do. If you plot the lines, okay, so basically what all of this is trying to plot the lines, okay, it's not doing anything special. You can go through and try to alter it. So we are basically trying to plot these lines. Now yes, so this is also maybe some practice for you. So sit down and try to plot them. You just use the tutorial. Okay, now if you plot them, you find that the 2-4 point is the intersection between those two lines. That means that that's the solution for that system. Okay, that means that that's the only point in space where they intersect, and that is how you solve the system of linear equations. So that is just one demonstration for you to get the whole concept. Now when you come to linear regressions, okay, linear regressions are also basically a set of equations that you have to solve, basically. So in linear regressions, what you are basically doing is you are trying to solve a set of equations to get a suitable answer. Basically, that's all regressions are about. Okay, just that the difference is in regressions you are doing iterative solutions, so you are solving iteratively all the time, and there are many solutions to maybe there are many approaches to solving regression. Okay, and then that's why I mean, we have a lot of different types of regression models. Okay, so let's do a quick example. So a quick example where we pick some points. Okay, so we are going to pick some random points 0, 1, 1, 2, and then 2 and 2.5. Now with these 3 points, we want to so if you represent them as an NumPy array, you know that they will look like a 3 by 2 matrix. Okay, and then we define a y, which is some 3 set of results, which means that will look like a target that will look like a target vector, right? And then we define theta. In our previous lessons, we tried to find what theta is. Theta is trying to find the angle between two lines. Okay, so when you try to find the angle between two lines, you mostly use theta. And what we want to do here is we want to solve it, but then when we solve it, we want to find the line of best fit. Okay, now the difference here is that all of the points you have, you don't have one line that goes through all of them equally or just at the right point. So the best thing you want to do is you want to draw a line that approximates them as best as possible. Okay, so that's why you need regressions. Okay, so from here you can solve this manually, but you can simply use your models to do. So basically we use .solve. So just know how to use the NumPy language here. So if you do numpy.linux.solve x.t, now you know that what was your, so x.t times t comma and then x.t times y. So that means that your t there is what you're trying to find. Okay, that's the variable we are trying to find. So once you just put it into NumPy to solve, it does all the computations. Now if you're doing this in real life, you probably have to maybe go through some least squares and a number of things before you get there. But NumPy will simply give you the line of best fit as y is equal to 1.0833 plus 0.75x. Now this one approximates a line that all of these would most likely fit through. Okay, so that's very great. Now there are other examples. So this one we call it a perfect line. The next one, so for instance, if we take some x data, so we set an array of 0 to 4 that data, and then we set on the y side, we set also an array from 3 to 35, the odd numbers, to 11 in that order. And then we do x equals numpy.column stack mp.once, and then so basically trying to understand. So mostly when you are doing programming, right, at this level, try to understand the syntax. I think that's what Mr. Siama was trying to talk about today. So try to understand the syntax. When we do this, what are we trying to do? We are trying to match the pairs. Okay, we're just trying to match them, and then again we are trying to also find the solution to them, which is the t. Okay, which is the efficient solution for all of them. So the intercept column goes to 0, which is 0. So theta 0 of 0 and then theta of 1 will be equal to 3 and 2. So this is where you have like just some exact numbers fitting. So this is a very good fit. You don't have to do much about it. But then it doesn't always work that way all the time. So let's try to visualize intercepts. Okay, we've already visualized one intercept in the previous. So in the previous example, that was one intercept we tried to visualize. Now the next thing we want to visualize, and then again, this whole syntax here is also for plotting. Like I showed you the last time, you don't need all of this to plot a graph. Okay, you can take some of the things out and it will still work. So you can take out legend is always good to keep. The limit, so this gives you a y limit. This is a title. You can remove font size, it doesn't change anything. You can label the axis. You can remove this line, the h line. You can remove it. It identifies features for the x-axis. You can remove it. It doesn't change anything. You can remove the grid. But mostly some of these things you like to put them there.
So if you do grade equals true, you can remove alpha equals 0.3. So some of these lines of code, you can actually reduce it to look very simple. Okay. So this is your homework. Try to play around with that. Now, why do we need a column of ones? I think this is what I think last week. I'm sure he taught it in the last week lecture. Now, depending on a moment. Yeah, sorry. So back to it. So it says, why do you need a column of ones? Okay, why do you need a column of ones? Now, in regressions, right? Mostly you don't want your model to pass through zero. Okay. Now, what does it mean to pass through zero? Can anyone try to visualize it? Yeah. So let me make it open to everyone. Um, what would you think would happen if you have your model passing through zero? So this is a question again for analysis. Okay, so I think with this one again, let me give you a timer again. So 2 minutes, I think that should be enough. So again, I'm giving you 2 minutes. Try to figure out why is it that in regression, so this sort of regression lines, it's not as good to have your line passing through zero or passing through the origin. If I say zero, not too correct, but you don't want it to pass through the origin, and why that's why you need a column of ones. So let me give you 2 minutes. Okay, 2 minutes. Try to brainstorm this. You can use any model you want. You can read it online. But 2 minutes time, I'll ask for an answer, and I think I'll try to take a different person who hasn't spoken today. So your timer starts. Let me see. Okay, so let me set your timer for you. Yeah, so your timer starts now. I hope everyone is searching. So everyone should be searching. I think when I'm done, I should just look at a name and call someone. Right? Okay. I hope everyone is actively searching. Yeah, so I think for those who are asking for real examples of machine learning models, basically you need to understand the basics before jumping to using actual models. So basic things like this, you understand why it's necessary. Yeah. Okay, I think I have a message. Emmanuel, are you done? Let me see. Um, I got lost with this question. Okay, so Emmanuel, what we are doing is that, okay, let me take you back a bit. Okay, so we are talking about visualization of intercepts, right? The intercept column. Um, now, I think I just skipped this a bit, but let me just read it out for you. So it says that the column of ones in the design of matrix allows the model to learn a y-intercept, that's a bias thing. Okay, so without it, the model will be forced to pass through the origin 0, 0, which is rarely correct in real world data and leads to a systemic biases, right, in predictions. Now, okay, okay, can you still hear me? Okay, is your time that elapsed? Okay, great. So basically, what I'm trying to ask is that why do you? Okay, I think that goes back to answer the question about biases. Okay, but I wanted you to figure out why was it necessary that you have column of ones and then making sure that it doesn't always pass through zero. Great. I think Bismarck. Okay, Bismarck. Let me hear you again. If you got the question.
Yes, yes. I got the question.
Great.
So when it passes through zero or the origin, so it means that we will not have any intercept, which also means that when we visualize it, most of the points will not be on the line of best fit. That's if it passes through the origin.
Great. That's good.
But if the regression line does not pass through the origin, we are more likely to have a more accurate prediction.
Good. Good. Did anyone else find something? I want to find someone's views. So, Bismarck, that's very good. Um, Manal, I've not heard from you today. Manal, are you there? I want to hope you can hear me. The Bismarck. I think I stopped sharing my screen. Okay, let me share my screen again. Okay, I think I'm back. Manal, would you like to come in? Okay, Esther. I want to hope you can hear me first. Okay. Okay, so can you hear me? Okay, great. So, Manal, Esther, Emmanuel, can I hear you? What did you find out? Hello, people, can you hear me? What did you find? Hello. Okay, if you can hear me, make a reaction. Let me just be sure you can hear me. Okay, good. Something from Emmanuel. So Emmanuel says that we need a column of ones in the design matrix. The line of best fit must not be forced to pass through the origin because most reward data do not start at zero. So forcing the model to do so introduces biases. See, that's good. So one thing you need to understand about machine learning is that there are biases that can come into machine learning. Okay, and then if you look at machine learning, I think there are a number of times where people have complained about biases like systemic race bias, racial stuff. Now, even though some of those things can come from the data you give, it also comes from how you manipulate the data. So the bias can also come from the mathematical basis. So that's where we see that allowing the line of best fit for your model to pass through, or your regression model to pass through zero, right? It introduces these biases. So understanding that means that if you have any model, you would like to really check the regression, right? You really like to make sure that the regression line is not passing through zero, because that's not very good. You have no intercepts, and that's wrong. Okay, so in real world applications, that doesn't work at all. Now, there is an extra step to this whole thing of regression. So what we just did was linear regressions. Okay, now you can have polynomial regressions. Polynomial regressions are just like you have a lot of points. Okay, you want to draw a line through them, but then the points are not in a straight manner at all. They are, let's say, some way curvy. Okay, so you might want to draw some sort of polynomial line through it. Okay, quadratic equation, things like that can best describe the model. Now, the good thing about this is that if you're doing actual mathematical calculations, like actual hands calculations, you do a lot of steps, you do a lot of iterations to get to that stage. But when you're using NumPy, you basically do the same thing again, right? So it's the same process as we did for linear regressions. Okay. So let's just go through this example. So NP is equal to colon the stack that. So these are from the data we already had, the X data. I think we already had that first. Let me see if I'll find it for you so that you're not confused. I think I went so far. Okay, so this is our x data. Okay, all right. So this is the x data, the same data we used, and then okay. So basically, what we are trying to do is that we are trying to create a new vector. Okay, a new variable. Call it x quadratic, and then we pass it through with the ones we created, and also we pass it through with the ones we created, the squares of the ones we created. Okay, so that sort of complicates things a bit. And then theta of the quadratic equation would be trying to solve them with the solutions, right? So each solutions of t, and then we can print out the line of best fit for that too. Okay, can print out the line of best fit for that too, and would have that. Okay, now let me show you something here. I think I want to make sure okay, so just to understand more about, I know that the lecture last week ended on linear regressions. Everything you just did was linear regressions, but understanding this one also helps. Okay, now in maths you have to do a lot to get your polynomial regression line like this. Okay, but with NumPy you don't have to do a lot. You just have to use the code. Okay, now look at the blue line and the green line, and then all the dots you have. So all the dots you have are the data points. Now the data points are all the those 5 points you were given, and then the squares of those ones. Okay, so nothing special. So I want you to look at this and then tell me the difference between these lines. So the linear fit and then the quadratic fit. What are your observations? I want someone who hasn't spoken today. Let me see if I can get someone to do it. Okay, so Esther has also answered regarding the force in the line. She says force in the line it distorts the fit, especially if the actual data point cluster away from zero. So this leads to large residuals, so large errors, and a very terrible model. That's very good. So at least now you understand what models are. So the next step would go to be building models and then trying to understand them. Yeah, so my question, what's your observation about these two lines? Emmanuel, I think Bismarck, I've heard from me today. Esther, Manau. Someone like to talk? If you like to unmute your mic, you can unmute and talk. I mean, like just your observations, not anything too technical. What do you observe about these? Okay, Mano. It looks like you guys prefer to type than to talk. Okay, anyway, that's still okay. Okay. So you see that your linear line of best fit is just okay, yeah. Bismarck, let me hear you again.
Fit, I realize most of the points are not passing through the line. But for the quadratic, we can see that most of the points are either close to the line or on the quadratic fit.
Yeah, that's good. So that's basically the observation I expect all of you to be making. Now, note that if you remove this green line, okay, if you remove the green line, it will still look like a good line of best fit. It will look like a good one. But with the same data, using a better regression is better. So like, let's say with the same data, okay, with the same data point, if you use the linear regression, you get some line of best fit. You can use that to build your model. But that would be wrong, okay? So if you estimate it better using a polynomial regression, then you have a better sort of a better trace. And then let's say if you go further than a quadratic, then you get something better, way better. Okay, now let's proceed. Linear coefficients, that, and when you're doing quadratic equations, you get the quadratic coefficients too. Okay, so basically that's it for that part. Okay, now let's try to today I'm rushing a bit because I have to I have to leave in a moment. That's why I said I sent the notebook earlier. So I hope you identify this guy, right? I mean, I'm guessing this side is supposed to be understandable for everyone. Everyone is supposed to understand this part, right? Let me see. Who haven't I heard from today? Manao, I keep mentioning your name. Are you there? I guess you identify this slide, right? You understand this part. Okay, Emmanuel. I guess you guys understand this part, right? Okay, so what basically you have to do at this part is you have to wait for us. Okay, so just wait. You can try to figure out how to do the coding later on, but this is just going to be a whole summary of what we've been trying to do with this. Okay, now so with this one we've gone ahead to use Seaborn and things like that. I don't know if you've used them, but don't worry, you get to understand them. So once you have the notebook, you can play around a bit. So don't try to understand the code much. I'm just jumping a bit from it. Okay.
It's not easy to be TAT.
Okay, so let's get back to it, guys. Sorry. Okay, so this is what we're trying to do. So the first part, okay, finding a determinant and using that determinant to scale up, like as in to transform a square vector, the sort of. Okay. Yeah. So we had a vector with determinant of 3, then and we had a unit square vector. Just say square vector, a square matrix. Okay, which was that. So when you try to do transformations, okay, what happens is that you can enlarge and distort what you already have. So mostly by scaling up or scaling down the matrix you have. Now note that I'm saying matrix, but in actual sense that's like data. Okay, that's actually some data. So when you try to scale up or do things like that, transform your data points, you get something totally different. You can distort it a bit. Sometimes it can be good for some reason, sometimes it doesn't work so well. Now the next part we're trying to talk about is intersection of lines. Now when you have intersections of lines in models, okay, an intersection represents a solution. So no matter what equation you have, intersections of lines would mean that that point satisfies both lines, okay, or both equations, and that's one point you can start working from. Mostly you want to find similarities between things, okay, so intersections do help. Intercepts, okay, so we've mentioned intersections that help. Now next is intercepts, and that's where I made you guys research on why you don't want your line to pass through 0, and then the whole idea is about intercepts. So intersections are important, intercepts are also important. So intercepts are important in ensuring that there are no biases, and intersections are important because that has to give you a solution to whatever you're trying to solve. Okay, now next is so we did linear regressions today, but additionally you need to understand polynomial regressions, because polynomial regressions better estimate the line of best fit than linear regressions. And as you can see, if you have a data like this, a line of best fit can look like this, which is a bit too terrible. But then if you look at the polynomial regression, that gives you something. Now understand that this is a quadratic polynomial, okay. You can have further types of polynomials that would estimate this way better, okay. So you can have polynomials that would do all the curvy way through it, and then it'll still be a right polynomial, and that can be a better approximation for your model, okay. So how is this important in real life? In real life, I've basically told you that when you're doing model solutions, so if you are solving models, basically use Gaussian elimination method, okay. That's lower upper decomposition, which is very good. And then some of them solve, which is good. And then also this third one, it is good when you're doing regression. Okay, so there are a number of things that come into training models, and basically try to think about it like if you've never built a model before. Okay, try to look at it like all of these are data points. Okay, let's say this could be the age of someone with respect to their height. Okay, so all of these are data points, and then you want to understand, you want to draw a line to pass through to pass through those points as good as possible, so that when you have another new person who has, say, um, on the horizontal axis, let's say they have, okay, let's just do this, that on the vertical axis you have the ages, okay, ages of people. On the horizontal you have their height. Okay, and you've plotted the ages and heights of people. I think age is not a good thing. Let me say weight and height. Okay, so let's say on the vertical you have weight of people, and on the horizontal you have their height. Okay, and you're able to plot across. Now what you want to do is you want to find a line that best describes all of them. Of course you can't find one line that does all of that, but you can find a line that better approximates that. Okay, and then what I'm trying to tell you, that linear regression does not solve models so well. Okay, so linear regression, as you can see there, is not so good. So the polynomial regression gives a better estimation. Now in the future, if I give you someone's horizontal axis value to be, say, 3, that would fall somewhere around here. Now what would be the corresponding y? You get that? So that's where you need to have a good quadratic equation. That way you can just plug in and then find your values. As simple as that. So that's all what machine learning is about, really. It's about trying to estimate the unknown from new data using knowledge of previous data. Okay. So these are mini exercises for you. So try to solve the Cramer rule by hand. It's not too complex, so you can do that. Try to do the lower upper decomposition LU factor on a 4x4 matrix, random matrix. So choose the matrix of your choice and then do LU factor decomposition with it. Try to find the LU factor of it, and then maybe just try to fit a quadratic equation on some data. So you can generate some data, and then, or maybe you can get some random data online and then try to estimate it with a quadratic equation, and then and then you can compare those 3 methods and see which one works best. Okay, now with today's information, if you want fake data, if you want fake data to use for your practice or anything, you can use generative AI models. I think that's what Mr. Sema was saying, that you can use things like ChatGPT. Okay, you can ask it to generate fake data for you, and then it can do that and use that for your training. Okay, no, not training at this point. So just say you are trying to do a regression through it. So this time, just see it as regression. Okay, I think in the future lectures we would move on to training, but for now, just look at it as regression. You're trying to draw lines through them to understand how do you predict the next values. Okay, so I think basically that should be all for today. Unless someone has a question, I'd be glad to answer. Does anyone have any question at all? And you have the notebook, so please try and go through everything. And you have a discussion group just in case maybe you are working through something you don't understand, and there are practice examples inside so you can solve them. But just in case you are going through something you don't understand, you can always let me know. Does anyone have question they would like me to answer in the lecture, in this lab session, no lecture? Anyone? Is anyone confused about anything? Yeah, Bismarck.
Gaussian elimination that much. Yeah, I didn't understand the LU. I mean the code.
Okay.
So please, if you can just spend some 1 minute going over the Gaussian elimination.
Let me go back to that place. Okay, are you familiar with how to do LU decompositions by hand? Yeah. Or this is your first time seeing it? Where did I put it?
It's my first time seeing it.
Okay. That's fine. Okay, so um, one thing you have to understand about early decompositions is that I'm coming. Let me get you.
I'm trying to locate where I wrote in, which part of the code, but I'll find it very soon for you. But let me show you this, so that you appreciate it more. Decomposition. Okay, I think this should do the job. Okay, so I'm sharing a new tab.
Okay, great. So you should be seeing this tab by now.
Now, what I just said was early decomposition. Now, there's a method for solving systems of linear equations. Okay, sometimes you can use it for 3 by 3, 4 by 4 matrices, and all of that. Now, this how it works. Okay, so you have a set of vectors. You have a matrix. Okay, so this is a 3 by 3 matrix. You have your unknown factors, and you have your known vectors. Okay. Now, early decomposition basically, I think, so it starts with forward elimination and then backward substitution. Okay. So forward elimination, what you're trying to do is mostly you try to find ground commonalities. I don't know if that's a word, but common things between the first line and second line. Okay, so that you can eliminate this factor. Okay, so you can eliminate A21, and then the next one you use this one and this one to try to eliminate these two. Okay, now eliminating these two, you now end up with one, that and that. Now try to look at it just mathematically, that if you're able to do that, if you're able to do this decomposition and then get rid of this and these values, so they have 0 for those spots. Now you find that A33 times X3 will be equal to B3. So that means all of a sudden you have the answer for X3. So that means X3 will be equal to B3 on A33. Now if they are scalars, which they are mostly scalars like numbers, okay, you find the value for X3. Now after you find the value for X3, you can come here. Okay, so at this point you would have A22, so that would be A22 times X2 divided by that times that will be equal to these ones,
and that way you can substitute your X3 into it and then get your solution, and then go back and you'll find the X1. So it's basically like you eliminate some of your matrices, like the first one on the second and then the first two, and then after doing that elimination you do like a backward substitution to get your answers for each. Now I really recommend that you go on YouTube to try to solve this manually. Okay, so that will be part of maybe your assignments for the week. So try and go on YouTube, try to solve these manually, like just try and solve them with your hand. It's not complex. Okay, now when you do that, let me get back to the code and show you
how it's working. Okay, I think where are you? Yeah, so back to this. Oh, okay. I think it was way up. Okay, so I think
this is where we have our early decomposition. Okay, I think this is where the code came in. Now when you do the solving by hand, you realize that it's not difficult, it's just a bit long. Okay, it's not difficult at all, it's just a bit long. Now what you want to do using this code, okay, so basically what happens here is you want to do your first stage. So the first stage is the forward elimination. They call it Gaussian elimination too, it's the same thing. You can just use So SciPy is a math library, science Python. It's a math library that has functions and curves and all of things like that. So from SciPy, we want to import LU factor. LU factor is some already encoded um, model, or should I say method.
Please your
Can you hear me?
please your screen is not showing the code. We are still at
Okay,
the
okay. I'm
Google.
still showing this. Thanks for reminding me.
Yes.
I forget. Sorry. Okay. Can you see it now? Okay. So I'm back to this page. Okay. So I'm trying to see, let me just rewind again. So I'm trying to say that SciPy is a library for you can use it for mostly maths, waves, equations, stuff like that. And then you can import a number of methods from SciPy. Okay. And then if you just have scipy.linux alone, you can import LU factor and then LU solve. Now these automatically solve what you do by hand manually. LU factor solves for finding the forward elimination. Okay, so it finds a factor that removes the so it finds a factor that removes the A21. I think I showed you the first matrix on the second row, and then the next two on the last row. So this factor finds a way to remove them and make them zeros. Okay, and then the LU solve does the backward substitution to solve for everything. Now these are summarized forms of the actual mathematical process. Okay, I hope you get that. So if we say so if you want to print the main matrix, okay, so let me just show you. So after the whole process, okay, um after the whole process, it feeds you, or let's say it pops back an answer based on the solution. Okay, after it has done all the forward elimination, backward substitution, and then so so this one gives you your, what do you call it, whether it is true or false. Okay, so you can get rid of this line, it's not too important. Okay, um where's my dash? Oh boy, what happened to my keyboard? Okay, so basically you can comment those whole line. You can comment this whole line, it's not so important. Now what's important is this place. So you want to print XLU, that is the lower upper decomposition of that. Now you find that when you are at the solve side, you pass your LU through it, and then you pass your pivot through it. Okay, and you pass your B2 through it. You get that? Now this automatically solves it and then prevents you from going through that whole long mathematical solution. So my recommendation is to try to understand that. Maybe you can understand it first by appreciating how the main mass works. Okay, so try to go on YouTube, find a simple question, and try to use the forward elimination, backward substitution to solve it. That's the Gaussian elimination method. And then when you do that, now just come back and then try to understand what's happening here. So this first factor tries to make second row first vector 0, and then tries to make the last row first two vectors 0, and then that allows you to do simple substitution. Okay, yeah, so I don't know if I complicated things in this explanation. The code tab is not
It's
showing.
I get it now.
Who said the code tab is not showing? Has it been sorted?
Yes,
Okay, okay, okay. Yeah.
but
So
I
this
think
part,
you are
did you
back
get
to
it?
the main. Yeah, I get it now. I get the explanation
Okay,
now.
okay. Great. Yeah. So basically, sometimes to understand it, you need to appreciate the maths first. Okay. Yeah. So I think this is something all of you can actually do. It will be really helpful. Okay. Well, does anyone have any question again? Okay.
So if you don't have any questions, okay, I recommend you go through the notebook. Try to make it as comprehensible as possible. So try and go through the notebook and then yeah, try to see what you don't understand. If you don't understand anything, put in our discussion group. Um, yeah, you can put in our discussion group. And I know you probably have other ways of reaching out, so that should still work. Okay, so if there's anything else, if there's nothing else, I would like to. Or is there anything else? Let me just give you the time because you have some time to spare. Is there anything else anyone would like to talk about? Okay, so nothing. Okay, so if there's nothing, I'll leave you with the time left. So that you do something too. So use the time left. Okay, use the time left to come and solve these ones. So let's start with the small ones. Okay, so use the time left to come and solve these. Where is it? I think I wrote a question here. I'm not sure. Cost elimination, gold standard. Okay, great. So I have other examples here. Okay, so try to solve these ones using any of the methods you would have learned so far. Okay, so try to solve these two. Maybe you should try and solve this one with one different method and then solve this one with another different method. Okay, so you can use the time left to do that. So try to program it, go back, look at the other lines of code, and maybe just try and copy and learn from that. Okay, so I'll leave you to do that if there is nothing else. So thank you very much for coming today, and I hope you hope to see you tomorrow in our next lecture where we are going to dive really into the main machine learning stuff. All of these has been groundworks, which is very important. Okay, so thank you once again, and enjoy the rest of the lab, and also have a good evening. Bye bye.